Thanks a lot. Thanks, Heinz, for the introduction, and Jean-Marie and the other organizers for the kind invitation. It's always a pleasure to be here. Despite the weather, I think it's a great place no matter what. The talk today will be on local density approximation. This is joint work with Mathieu Lewin and Elliott, and it's really connected to two papers we wrote, one appearing last year and the other one more recent. It's available on the archive. Okay, so the basic object of study is density functional theory, as I guess most of you know very well, the objective of density functional theory is somehow to express physically relevant quantities, the simplest being ground state energy of some complicated quantum system, in terms of the particle density only, right? So in general, one has to consider a quantum many-body problem where the main object to find is the many-body wave function, right? So think of a psi of n variables, n being the number of, say, electrons in the system, and n is typically very large. Whereas the particle density is a much simpler object, right? It just looks at the density distribution, which is sort of a one-particle marginal, right? You just look at the square of the electron and you integrate out all but one variable, right? The usual normalization being n, so that the integral of rho is n, and you interpret it as the particle density. Okay. I will suppress, say, internal degrees of freedom like spin here in my notation. They can easily be included, but for simplicity, I don't explicitly mention them here. Okay, now what is the basic object? Well, you could say you could formulate sort of the fundamental density functional in the way going back to Levy and Lieb, and sort of known as the orbital free formulation of density functional theory, as just saying, well, I get a density functional out of the many-body problem by simply say if I look at the ground state energy, right, I first minimize under a constraint that all the wave functions have a given density, then I get a function of the density, and that's sort of the fundamental density functional, right, which is called here the Levy-Lieb functional. Maybe I should actually write down sort of the fundamental Hamiltonian, right, as considered here. It's sort of implicit on the slides, but it's not explicitly stated, right? So H V N, so this would be typical Hamiltonian if you wanted to study, say, a large molecule, or maybe you want to study electrons in a solid, and the simplest model is obtained via the Born-Oppenheimer approximation. So you just model dynamically the electrons, so you have n electrons right, with the kinetic energy just given by the Laplacian in the usual units, and then there is the interaction between the electrons. And now what actually really defines the model is sort of the external potential. So if you think of a large molecule or so, right, so you have an external potential given by the interaction to the nuclei, but abstractly I just write it, right, it's a one-body potential of the form V of xi summed over I, right? So that's the fundamental object, and if you want all the details of the model are in the choice of the potential V. Whoops. All right. So now, if we take this Hamiltonian, right, say we want to find the ground state energy, which is called EV event here, we just take the minimum over all normalized wave functions. And of course, I can do the minimum in two steps, as indicated here. I can first minimize over all wave functions psi, having a given density. And this naturally leads to the Levy-Lieb functional, where the potential sort of is separated out, because the potential, you see, only sees the one particle density anyway. Okay, so the contribution of the potential to this density functional is really trivial. It's just exactly the integral of the potential against the density. What's the non-trivial part is the one coming from the kinetic and the interaction energy. So that's given here. You just minimize this part, which is called H0, right? You just remove the potential. You minimize overall wave functions at having as a constraint this given density rho. Okay, and this gives you a function of this density rho, which is of course very complicated. I mean, there's no hope to actually compute this function, because to compute it, right, you really have to solve a many-body problem. Okay, but fundamentally, that's just what the object is, it's naturally defined on all densities, say, right, positive functions, integral n, and if you assume that it has finite sort of kinetic energy in this way, then this is a well-defined object, right? So you can convince yourself that for any such density, there's at least one many-body wave function having this density, and therefore this is sort of a well-defined object. So this was studied in detail by Lieb in the early 80s. So now, so this is our main object of study. As I said, there's no hope to investigate this exactly, but it's sort of the basis of many approximation schemes, and maybe you could argue it's sort of the basis of sort of applied density functional theory, say, as done in quantum chemistry. So what we are after, we wanted to investigate what happens if the density is somehow slowly varying, right? That's sort of this local density approximation. So here is a picture. I should acknowledge actually all the pictures on my slides were made by Mathieu. So here is sort of a picture of what you should have in mind. You have a density which is very slowly varying. So in other words, say the typical length scale set by the density itself, namely the mean particle distance, right, would be much, much shorter than the variation, the length scale given by the variation of the density itself. So locally, if you zoom in, the density looks essentially constant, right? That's a situation we would like to describe. And then the local density approximations amounts to the following. Well, you would argue that this energy function should essentially be local, except for a sort of a trivial non-local term, namely the Coulomb interaction of the sort of density distribution itself, right? Clearly we're describing particles with Coulomb interaction, so there's clearly a long-range force, but this long-range force we describe sort of classically. Think of rho just being the charge distribution of the electron, so there should clearly be a classical, the direct contribution to the energy, this classical Coulomb energy. But if we subtract that, then the rest should be essentially local. That's what this approximation sign means, right? So local meaning it's just given by a function that depends on the density at the given point x, and then we integrate over x. This would be the local density approximation to this functional, or more precisely to the functional where the direct Coulomb energy has been subtracted. Okay. Now what should this F be? Well, F is simply the energy of a homogeneous system, because it's the local density approximation, right? The density is local approximated to be constant. So F should simply be what you get if you look at the system at a constant density rho, right? The so-called homogeneous or uniform electron gas, right? So I have more on this on a later slide, but let me actually start maybe right away by explaining the main result, which is sort of a justification of this local density approximation in the case of slowly varying densities. Okay, so here is the main theorem. We look at the Levy-Lieb function, or actually we look at a sort of convex hull of it, so the grand-canonical version. I'll comment on this in a second. That explains the tilde on it, so it's not quite the functional I wrote down. And we subtract the Coulomb term, as I said, the direct energy, and we subtract then what we expect the result to be, namely this local energy, the integral of this energy density of the uniform electron gas evaluated rho integrated over x, and the claim is that this difference is small indeed if the density is slowly varying. And now how is this quantified here? Well, there's one term here on the right side which is not actually small, right? It's again local, it's a function of the density, it's linear for small densities and quadratic for large densities. This is a priori not small, but it comes with an arbitrary small constant in front. So this epsilon is actually indeed a free parameter. You can choose it as small as you want. So you can make this term small. Of course, the price you have to pay is that the two error terms here, they will blow up as epsilon gets small, but they are manifestly small if rho is slowly varying, in the sense that they are actually just functions of the gradient of the square root of rho. right? So a slowly varying density would have this term. Here's a H1 norm, and here's a fourth power of the gradient. If these terms are small, we can indeed choose epsilon fairly small to have these expressions still reasonably small, and then this term will be small too. Okay, that's the natural interpretation. Okay, so in that sense, if the density is slowly varying, by optimizing over epsilon on the right side, we will get something small. I should say that these powers here, I mean, these are sort of rather crude estimates. This is by no means optimal, as you, I guess, would immediately guess when you see something like a power 15 showing up. This is due to maybe our crude way of estimating things, but at least I think it's sort of a first result of this kind. Okay, so a few comments. This is related to what I just said. So actually, not only is this not optimal, it's also not in any way natural. And in fact, if you look at our proof, this can be replaced by other powers. This comes from some Sobolev inequality where you have some freedom on how you choose the exponents. And here we have sort of an exponent 1/2 and the p equals 4. But actually, this could be replaced by different exponents, different thetas and different p's here under this constraint. That's just how it naturally comes out of the proof. Now I should say a few words on what this F tilde actually is. So this is, as I said, the convex hull of the Levy functional. Right? I remind you, here is the definition. This functional is not actually convex. It has no reason to be convex, so we can look at its convex hull. So what this actually means is simply that instead of minimizing over wave functions psi having this given density, we allow mixed states, okay? Then actually it's easy to see that we do get a convex functional, okay? Because then you're minimizing over something, you have a convex set. So we minimize actually over mixed states, and then we also mix over particle numbers, so we really do it grand-canonically. So maybe I'll write this down here. So the F tilde LL over rho is just minimizing over density matrices now on Fock space, okay, of say trace H0 n gamma, where, the density of gamma is equal to rho. Okay. So it's the natural generalization to mixed states on Fock space, so we allow also the mixture of different particle numbers. It's just the average particle number is naturally fixed by fixing the density anyway. Okay, so this is slightly smaller, clearly, right? We're minimizing over a larger set. We don't expect that it makes any difference as far as the theorem is concerned, so it should naturally hold in exactly the same way for the canonical version of the Levy-Lieb functional, but we do not know how to prove it, and I will actually comment on that. It's simply, for technical reasons, it's much easier to work in a grand canonical setting. And here's a third remark. So now we could, for instance, look at very slowly varying densities. By that I mean simply densities that vary only on the scale of the size of the system, right? So think of a system of having a density locally of typically order 1. So that means if you have n particles, the system will have a linear size of order n to the 1/3, just a second. And therefore, we could take a density, which is of the form some fixed function sigma of argument x n to the -1/3, right? So this density would have now integral n, and then we could ask how do things scale with n, and if you plug it in, you see that the direct term scales like n to the 5/3. The local density term scales like n, that's the extensive term, and then you could ask what is the error term we get for such a function, and actually if you plug it in and you play with these powers, you see it's order n to the 11/12, but the point being that this is less than 1, right? So we get a non-extensive correction, this being the extensive term and this being the direct term. Okay, there was a question?
So in this grand-canonical picture, should we replace Hn by the Fock realization?
Yeah, so n, you're right. When I say n, of course, you should think of n being the operator n, right? So this is really, there's a sum over n's involved. So this is sort of the Fock space. This is the second quantization of the Hamiltonian in a natural way. Yeah, thanks. Okay, So now a few more words about this function f, right? I already told you this function f appearing is simply the energy of a homogeneous electron gas. So you can define it, for instance, this way, that, well, you look at the Levy-Lieb functional for a density that's essentially constant over a large domain, right? So you take a domain omega, take some nice domain, you scale it by a factor L, so now you have a big domain, and you just let the density to be constant rho 0 on this domain. Okay? Now that doesn't quite work yet because this is a quantum setting, right? So we cannot have discontinuous densities. We need something where the square root of the density is in H1, otherwise we have infinite kinetic energy. So we smear it out a little, so we take some smooth function of compact support and we just convolve with this smooth function of compact support, right? So now we have a system where the density, maybe I'll draw a little picture over there, right? So we have some large domain. Some distance of order 1 from the boundary here, here the density is equal to rho naught, the constant, right out here the density is 0, again some distance of order 1 set by this function chi, and in here, well, you have some smooth transition, so to say, from rho 0 to 0. Okay, and then, so you can look at this setting, and then you take the L to infinity, you look at the energy per unit volume. Of course, first you have to subtract the direct term for such a density, right, to have a thermodynamic limit. So you look at the energy per unit volume, you take this thermodynamic limit, and that defines F as a function of this rho naught. Okay, and you can convince yourself that this is a proper limit in the sense that it doesn't depend on which omega you started with, and it doesn't depend on how you smear out the density, so how you do this transition here from rho naught to 0, right? And so one can prove this, actually, one can prove this in greater generality than what is written here, and basically following at least ideas in this paper by Heinzel, Lewin, and Solovey, where they studied sort of general questions of existence of a thermodynamic limit for Coulomb systems. Okay, so that's the function f. Of course, we don't know this function either, right? So this is still, you have to solve the many-body problem for a homogeneous electron gas. But what we do know, I mean, we know certain asymptotics, right? So for instance, for large density, well, for large density, the leading term is the kinetic energy. So you'll just have the Thomas Fermi term, Thomas Fermi constant, sorry, this is hard to read. This is Thomas Fermi constant times rho to the 5/3. Right, so this is just the sort of semi-classical kinetic energy of a Fermi gas. That's the leading term. Actually, also the next to leading term is known. That's the exchange correction. So there's the Dirac constant CD times rho to the 4/3. These are the first two terms in an asymptotic expansion for large rho. So this is known since the work of Graf and Solovey on the Gellium problem. Higher order corrections are known in the sense that they are conjectured, they are explicit conjectures in the physics literature, known as the Gell-Mann-Bruckner formula, and going back sort of to this work in the 50s, the next order term is believed to be of the order rho log rho, and there will actually be some talks later this week concerning this problem. So that's the large density. For small density, you see the Coulomb term is the main one, right? Because in kinetic energy scale is like 1 over length squared, and the Coulomb like 1 over length. So at low density, the Coulomb takes over. That's the classical problem. There, the kinetic energy is negligible, and actually just by scaling, you know that the energy has to be minus rho to the 4/3 for small rho. Because classically there's sort of no other length scale anymore. But what the constant is, this is also not proved. It's known what to expect, namely at low density you will have a Wigner crystal, and you can then compute which crystal will give you the lowest energy, so what you expect is the number 1.44 here showing up for the constant. This is sort of a big open problem, but it's known that at least energetically it's not far off. There is an upper bound which matches it actually up to sort of 1%. This is due to Lieb and Nahnhofer, so again, for the work on Gellium. So this is the sketch. I mean, that's how the function roughly looks. It's minus rho to the 4/3 and then it's rho to the 5/3. It's drawn here completely smoothly, but it's also known, or it's expected not to be exactly smooth actually, because there are phase transitions in this system, right? So for low density, I already mentioned the concept of Wigner crystal. There's supposed to be crystallization, and eventually at higher density the crystal will melt and you have more of a fluid. If you include spin, then you also expect a phase transition between the ferro and the paramagnetic phase. In fact, here I have a sketch of what is predicted numerically for the phase diagram of this system. Here's temperature, so we're always working at 0 temperature, so only this axis here is relevant for us. But you see expected low density crystallizations. You have a Wigner crystal, eventually it melts into a fluid, but you still have a transition between actually a polarized so spin polarized fluid or an unpolarized fluid. This is what is expected, but this is all numerics. I mean, there's no mathematical result in this. But all of this is in the function f, right? So I'm just warning you, this f is still a complicated function. We know it's asymptotics, but it still has a lot of very interesting structure. Okay, so here is sort of a more of a remark. So in practice, what the quantum chemists are interested in is what they call the exchange correlation energy, which is actually in notation here. It's not, you don't just subtract the direct Coulomb term from the Levy-Lieb functional, you also extract somehow the classical, if you want, the classical approximation to the kinetic energy, right? So again, the Levy-Lieb functional has the kinetic energy and it has the Coulomb term. So you subtract somehow their classical version, which is simply the direct Coulomb energy for the interaction, and there is the kinetic energy, which according to Cohn-Sham, I mean, you just define it in the same way as before, but just for the kinetic energy. So I think the original version is again in the canonical case, right? And then you'll talk about orbitals and so on. But here actually we do it for simplicity, or actually not just for simplicity, I mean, for technical reasons. Again, in the grand canonical setting, which would simply mean that you subtract the kinetic energy functional, which is simply obtained by minimizing the kinetic energy over all states with a given density. Right? And if we do this in the grand canonical version, it just boils down to this simple formula here. Everything is just contained in the one particle density matrix. Again, we do this grand canonically. So there's simply the constraint that gamma is between 0 and 1 from the Pauli principle, and the density is given by rho, and then you minimize overall one particle density matrix satisfies these constraints, and that's by definition T of rho. Right? And that term you should also subtract. Okay, and then you really have what the chemists would call the exchange correlation energy. Okay, and the remark is simply that, yeah, you can do this and the result is exactly the same. Okay, so the main theorem that I just presented is exactly the same if you replace, if you, instead of looking at this functional here, you also subtract the T, so you really look at the exchange correlation energy. And the reason is that there's a same or a similar kind of local density approximation for this kinetic energy functional also. And in fact, it's much, much simpler. That's why I display it here explicitly. So in fact, there are two inequalities of the following kind that quantify sort of the local density approximation for the kinetic energy functional. And what is the local density approximation? Well, it's just the semi-classical expression. It's this Thomas Fermi constant times the integral of the density to the 5/3. Right? That's what you would get as the kinetic energy, the minimal kinetic energy of a homogeneous Fermi gas, right? A non-interacting one. We just look at the kinetic energy. So to what extent is that correct? Well, so there are the following upper and lower bounds. In fact, the lower bound is due to num, and it's sort of, if you want, a generalization of the Lieb-Thirring inequality, right? I remind you, the Lieb-Thirring inequality says that the T of rho you can bound from below by a constant times the integral of rho to the 5/3. Okay, and it's a famous conjecture that this constant you can actually take to be the Thomas Fermi constant, but this is not known. Okay. What Nam has proved recently is that actually you can make this constant as close as you want to the conjectured Thomas Fermi constant. So there's a 1 minus epsilon, and epsilon is arbitrarily small. But the price you pay is again a gradient term with some inverse power of epsilon. But if the density, you see, is very slowly varying in the sense that this term is much smaller than integral rho to the 5/3, then indeed, after optimizing over epsilon, you have a very small correction to the semi-classical term. Okay, so the lower bound is known. What we managed to do is actually to prove the corresponding upper bound, which essentially looks exactly the same except for the signs, right? So the statement is that we also have an upper bound of the form rho to the 5/3 with the Thomas Fermi constant up to an arbitrary small epsilon, and the price we pay now with the plus sign is again a gradient term with an inverse power of epsilon. So this is, of course, contained in our main result, right? Because the main result concerns the Levy-Lieb functional, which has both the kinetic energy and the interaction term. So this is just the kinetic energy, and it's actually much, much easier this way. So I thought I'd actually show you the proof of this inequality. It's just a few lines, really. But it's still non-trivial because, you see, it's quite difficult to work with the constraint of having a given density. For upper bounds, you can use the variational principle. You can construct states of the proper kind, but you don't have much freedom because you're bound by definition, right? The formulation demands that you fix the density. Okay, so you cannot do sort of free variations. Whatever you do, you must not touch the one particle density.
Okay. This constant C is not the same.
It need not be the same, although in fact you can take it the same if you take the larger of the two. Right? So, but there's no, I mean, naturally it will not come out to be the same constant, no. In fact, yeah, this constant should be 0 ideally, the optimal one. That's what Lieb-Thering conjectured. Here, I'm not sure. Yeah, I guess this constant will have to be actually positive, right? And I guess one could even, there might even be a conjecture of what the best one is up to higher order terms, something like that. Okay. All right, so here, so I'll give you the proof of this upper bound here, and it's basically, well, it's a trial state argument, so, and it works in the following way. So first of all, just recall sort of the homogeneous system, right? So if you look at this one particle density matrix, which is just a projection onto the Fermi ball, right? So you give yourself some T, which is the density, that's why it's sort of written with these particular constants. So T, that is exactly the density. If you look at the projection onto minus Laplacian being less than this number, this is then the square of the radius of the Fermi ball. Then you see that this has density exactly T, that's how it's chosen, and the kinetic energy density is simply Thomas Fermi constant times T to the 5/3. Okay, that's just the free homogeneous electron gas. Okay, so now what we have to do, right, we have to find a one particle density matrix that has the exact density given by some function rho. Okay, and you see what does not work, you might naively think you could put in simply the rho here. In fact, you can do that, but if you plug in instead of T, the rho of X, right, you can do this, but it will not, this object will not have density rho. Right, so that won't work. So instead what we do, so we still start with this thing, okay, but now we sort of localize, we say that the T should be essentially the rho of X, but we can't do it exactly, but we do it with some localization function. So pick some eta. So think of eta being a function that's roughly supported at 1. Okay, so it's sort of a bump function that sits roughly at argument 1. So that means it localizes the T to be roughly rho of X. Okay, and so now we take this Fermi projection here and we multiply it from the left and from the right by this function, right, thought of as a multiplication operator. Right? This is a multiplication operator in p-space. From the left and from the right we multiply it by this multiplication operator in x-space. Okay, so this is now an operator, and now we integrate it over T. Okay, and now you see that if eta is normalized to have integral 1, then first of all, this thing will have density rho, because right, if we evaluate its density, then this guy will just give us a T, and we integrate over T, which by scaling just gives rho of X, okay, under this normalization. So this normalization guarantees that indeed the density of this gamma will be rho of X, and we have a constraint on eta because we want this density matrix also to satisfy the Pauli principle, right? So it should be less than 1. The guy in the middle is clearly less than 1, so we can drop it for an upper bound, can write it as 1, and then you see what is left is the rho scales out, because this is scale invariant, it doesn't depend on x anymore, and we just get the integral of eta times 1 over t dt, and this should be less than 1. Okay? So we simply take this trial state for any eta of this kind, and this will give us an upper bound. And that's it. Basically, now you just compute. You have to compute the kinetic energy of this term, so you naturally derivatives with respect to rho will appear. I didn't write this down, it's a simple calculation. And then you still have to try to optimize over all choices of eta given this constraint. Okay, so eta is somehow smeared, it's a smeared out function close to 1, right? It has somehow a bit more weight for t bigger than 1 than for smaller than 1. That's what this inequality is saying. So you have to play a bit, that's where the epsilon comes in, and at the end the bound just presented. I give you once more after you play, and epsilon is basically the size of the support of this function eta, then this inequality will come out. Okay, so this was sort of showing you the proof of this much simpler version of a local density approximation. The general proof is, I cannot give here, it's much more complicated, right, because I mean, it is a true many-body problem. Right, so we have to approximate, somehow even for an upper bound, you have to approximate this many-body system at a given one-body density in terms of a local system where the density is constant, but still the many-body state you don't know. Right? You still have to approximate it by the state of a homogeneous electron gas whose state we don't know. Right? It's this complicated thing that involves all the phase transition and so on. Right? So we somehow have to take this state, whatever it is, and then we have to sort of put it together and actually do this kind of construction of sort of squeezing it into the system in such a way that the given density comes out. And we have to get the exact density right, because that's what the Levy-Lieb functional demands. Okay. So I will just give some ideas in the proof. I mean, the key point is, of course, the locality, right? That's what it's all about, the local density approximation. So we want to argue that this indirect energy, so where I take this Levy-Lieb functional and I subtract the direct Coulomb term, I want to argue that this is approximately local. That's the first thing to understand. Okay? So what this means is, if you think of splitting space up, say tile the space with some boxes, omega j, and there will be some length scale which you're free to choose, which will have to adjust depending on the local density somehow, right? So that's the parameter L. So think of cubes of size L that will tile R3. Okay, and this L, as I said, is a free parameter, which at the end, I mean, that's where the epsilon comes in. We can choose L depending on some parameter epsilon. And we want to argue that given a density that somehow doesn't vary too much, it varies slowly, in particular on the scale set by this length scale L, then this indirect part of the energy should be roughly local in the sense that it should be approximately given as a sum, where I just evaluate the energy for a system at a given density rho, but confined now to one of these small boxes. Okay, so I want to say that it's local in that sense that the energy of the whole system is basically just the energy of a small system, and then you sum over all small systems. Okay, that's what this is saying. And now you see, if these boxes are small compared to the length scale on which rho varies, then rho is essentially constant on such a small box. So you would argue that indeed you can replace this energy for the system in a small box by the one where you just replace the density by a constant. Okay. And whenever you do any of this splitting, of course, since we're in the quantum setting, we have the kinetic energy, we always have to do some smearing out at the boundary, right? We can never allow discontinuities in the density. That's why I always sort of indicate this here with this convolution with some fixed, nice, compactly supported functions, such that these things are actually finite. Okay? And so that would be sort of the second step. Now we're down to a system with a constant density, and now we still have to compare this system with the one given by the homogeneous electron gas, which is its thermodynamic limit, right? This is what I had displayed a couple of slides ago, that if you take energy of a system with a constant density, right, then the energy per volume, this will have a thermodynamic limit, and that's exactly the F. But now you see that statement is not enough for us, right? We don't just need to know that we have a thermodynamic limit, we also have to quantify how far away from the thermodynamic limit. We really have to compare this difference, right? Because at the end we want a quantitative bound, not just a limit statement. So we need more than to know that this thing converges or is to leading order given by that. We actually have to control the difference. So we need sort of a speed of convergence, if you want, in this thermodynamic limit. That's the third problem. Okay, so a few words, I think, both for upper and lower bound, right? So we have a bound on the local density approximation, which means we have both upper and lower bounds. So for the lower bound, a key ingredient is an inequality that goes back to Graf and Schenker in the 90s. Which is really an inequality for just a classical Coulomb system. And it somehow quantifies this locality question I mentioned. And in particular, the sort of screening that goes on in Coulomb systems. So let me maybe first recall the statement. So we have again a tiling of R3 in small boxes, but it turns out it's actually important for this to work what the boxes are, and they have to be tetrahedra. It does not work with cubes. Okay, so here's a two-dimensional version of this, where you just have these triangles. So you tile R3 by some tetrahedra, say a priori they are of size 1, which means say volume 1, but then we scale everything by L, by some arbitrary parameter L. And the statement is as follows. Look at the classical Coulomb system with charges of values zi. Think of them plus or minus 1, although it doesn't really matter here, the inequality is completely general, but in particular there are positive and there are negative ones. Okay, that's indicated by the two colors here, the blue and the red. Also, that's not really important. I mean, the inequality is true no matter what, but it's only sort of useful, it's only quantitatively good if you have approximate neutrality. So you think of positive and negative charges. Okay, and then you look at the Coulomb energy of this charge distribution, which is just the sum over all pairs of the product of the charges divided by the distance. And the inequality says now the following, that basically you evaluate the same quantity, but only inside one of the tiles, right? So think of this triangle here. You just evaluate the Coulomb energy for these three charges in there, right? So there's, say, repulsion between the two blue ones, and there's an attraction between the red and this blue and the red and that blue. Okay, they will have three terms. That's what's written in the parentheses here. Right? You do the same thing, you sum over pairs Ci, Cj, divided by their distance, but only if both I and j are inside the same tetrahedron. That's the theta n here, right? So n labels the various different tiles here, and they are scaled by a factor L. So L times theta is just a tetrahedron of size L, and there's a G appearing here, which is actually denotes sort of averaging over translations and rotations. So it turns out that's important. So we don't draw a fixed tiling, we actually average over where we put the tiling. So there's a translation average, and there's also an average over rotations. Okay, but maybe neglect that for a second. So given this tetrahedron, you just look at the Coulomb energy for all particles inside the same tetrahedron. Okay, and then what you do is you sum over all tetrahedrons. So you don't just do this for this one, right? You do it for all of them and add them up. Okay, so the big difference is that there's no interaction between different tetrahedra. Now we only look at the Coulomb energy of the particles being in the same tetrahedron, and then at the end of the day, as I said, you have to average over translations and rotations. Okay, and then the claim is that's the inequality, that this will give you a lower bound. up to an error which is sort of small if L is large, meaning you have a 1 over L error, naturally from the scaling, it's 1 over, it's the 1 over length from Coulomb, so you have a 1 over L error times basically the number of charges, if you think the z's being plus or minus 1. More generally, it's the sum of the z squareds. Okay, so this is sort of a quantitative version of screening as far as the lower bound is concerned, that basically every charge, you only have to look what happens, so to say, for the interaction with neighboring charges. Everything that's sort of beyond the distance order L, you can ignore, and you will still get a lower bound up to an error that you can control. Okay, so this in practice will give you a lower bound. Now, you might ask whether the opposite charge, I mean, we only have electrons, right? But you should think of as the direct Coulomb term that we have to subtract, right? The locality is only true after we subtract the direct term. This basically gives you like a background of oppositely charged particles. They are now not point particles, really they're sort of a continuous charge distribution, but then you can just integrate over the location, say, of the blue particles, and that gives you something like a background charge distribution, which as I said, the origin of which is really the direct Coulomb energy which you have to subtract. Okay, so that's sort of one key ingredient, and gives you this approximate locality because it basically tells you you can ignore everything that happens outside a tile. You see also where naturally now the grand canonical description comes in, right? I told you that for various reasons we don't want to work in the canonical setting, and here naturally this comes in because we don't know how many particles there are actually in each tetrahedra, right? If we now take a many-body state, even if it's a pure state, canonical one, globally, then in every small tile, of course, the number of particles will fluctuate. Right? And we will also not have a pure state. In fact, there's entanglement, right? So the state will naturally be mixed. So this version, applying this inequality, naturally puts you within the setting of mixed grand canonical states. That's one of the reasons. Okay. So this is, was basically just one sort of ingredient in the lower bound. Now I want to discuss very briefly also the upper bound, and which is usually the easier thing, right? Because you have the variational principle, but also here it's far from straightforward what to do because of this constraint on the density, right? So we're given a density, and whatever trial state we pick, we have to make sure that it has this exact density, and we want to find a trial state that not only has this density, but it also gives us this approximate locality that for evaluating this indirect Coulomb energy, we can approximately do it in a local way by just looking at what happens in small boxes and then sum over boxes. Okay, so as I already said this, right, the main challenge is that we need a trial state with the exact density, and as I also already indicated before, we need to build a state that locally looks like the ground state of a homogeneous electron gas, which we do not know, right? This is a complicated thing. It might be a Wigner crystal or not, right? It might be spin polarized or not. We don't know. But whatever it is, that's what we need to take, okay? So the first thing you might want to try is you say, well, you divide space into small boxes, and locally in every box you use simply the minimizer for this homogeneous electron gas. Okay, but then the problem is how you're going to put these boxes together. Right? You could do it if you have non-overlapping support. Then you can just do tensor products, but then you will never get the right density because you will ever have holes in between, right? So if you confine the system to a small box, the density will go to 0 at the end, and you'll end up sort of with a density of this kind. Okay, but I don't want that, right? I actually want a nice density distribution. So how can I sort of put things together in such a way to end up with a definite density and still think of it as local boxes? Right? And that's again where sort of the mixedness, the grand canonical version comes in, because we can do this even if we have such a system. I mean, if we build a state that has such a density, we can now average again over translations to actually make it have any density that we want to have. I mean, at least you can see if you average this over translations, you actually manage to get rid of these holes in between somehow. Okay? And you have to do this carefully, because whatever averaging you do, at the very end you have to end up exactly with the density that you want. Okay? but so, I mean, I just sort of sketch what we're doing, right? Basically, we start with such a picture that we actually do tensor products, because that's the only thing we know how to do, of systems, of independent systems at different densities. And then we do a suitable averaging over translations. And actually, for technical reasons, we don't just average over translations, we also average over dilations. So we have to sort of wiggle a little with the size of these boxes. This way, we can obtain, first of all, a trial state with the right density, and then we have to, basically from this averaging, we have to control also the error on the direct term that we will get, on the Coulomb term, which turns out to be of the order of delta squared, where delta is the size of these holes. Then, well, one has to put things together, one has to optimize over error terms. It's a long calculation, but this is sort of a key ingredient. So this was basically just to convince you that this is a difficult problem. Even the upper bound is actually far from straightforward. Okay, so I'm actually a bit ahead of time, but I'm basically finished. So I'll just summarize briefly the result, right? So what we've done is given a rigorous justification of the local density approximation in sort of the fundamental density functional theory, in the sense that if we look at the Levy-Lieb energy, or more precisely its grand-canonical version, then we can estimate the difference between this energy and its local density approximation in terms of error terms that involve gradient terms of the density, and in particular are small if the density is slowly varying. Open problems I've basically already mentioned. I mean, the same result should of course be true for the actual pure state Levy functional I defined on my first slide, but for technical reasons it seems to be actually quite difficult to do that, even though the result should of course be the same. The error estimates we have are far from optimal, also already indicated that. In fact, if you look at this case, I mentioned the very slowly varying case where the density sort of varies only on the size of the system, then we got an error term compared to the main sort of extensive term, which was n to the, I think, 11 over 12. In fact, what you expect is something like n to the 1/3. So there's certainly lots of room for improvement for these exponents in the error terms. And these bad exponents come from the fact that we have to rather crudely estimate things, but it's not at all clear how to do things better. Okay, and then of course, I mean, big open problem is actually to understand physically what's going on, right? I mean, this is sort of a general statement that if you have a slowly varying density, then locally the system will basically look like a homogeneous system, but even a homogeneous system, but we don't really understand the important issues, like in particular, as I indicated, the phase transitions from a Wigner crystal to a fluid state and so on. I mean, these are sort of very big open problems in statistics and mechanics that I think we're very far from understanding. So I'll stop here.
Thank you very much, Rob. Are there questions or remarks? No questions. Well, maybe I try the same question that I asked before already.
What did I answer?
I mean, in your definition of the Levy-Lieb functional, you have this gradient of rho already. And your error term,
so in the,
I mean, as a hypothesis, but it doesn't occur explicitly, right? You said that the gradient in the last line.
Here?
Yeah.
Yeah, this is just naturally there, because if you don't have this,
yes,
then this f is naturally plus infinity. I mean, then you will not find a wave function with finite kinetic energy, right?
So you suppose this, but it never occurs there. And the same occurs then in the error term. I mean, could you think of enlarging somehow this function f to include also the gradient, and then try an optimal functional?
I'm not sure I quite understand the question. So I mean, at this point, you would just, if you don't want to put this condition, fine, but f is just plus infinity if square root of rho is not in H1.
Yes,
and similarly, as our main result, right, if this thing is infinite, it's still a correct inequality, it's just not very interesting.
Yes,
so,
but I mean, you don't subtract any term that depends on the gradient.
No. But of course, one thing, I mean, I think maybe I'm rephrasing your question now. You could, of course, argue that if you wanted to do better, right, if you think of this some sort of expansion, and this is, okay, this is maybe the zeroth term, that's a trivial term, that's the main term, but then, of course, there will be corrections, so even if it's slowly varying density, right, what is the main correction term? And then actually, if you go to the quantum chemists, they'll tell you that there should be a term like this, right? I mean, with maybe even an explicit constant, which should be the next order gradient term correction. In fact, that's the one you get from the kinetic energy. There's a different one that comes from the Coulomb, right? But this is now really going way beyond what we understand. It's sort of asking for the next term, and it's a valid question, but I think maybe many years will pass before we really understand this.
So what's the main difficulty in doing this? To include this also? I mean, why don't you try this?
Okay, I'm not saying we're not trying. No, I mean, but you see, the point is that the term that should be there is a next term. It's basically this term, but no epsilons, of course. And this term, if you think in terms of the scaling, is a term that's order n to the 1/3. Of course, I can write it down, but it doesn't say anything because all other error terms I have are much bigger. So I can include it, but I don't have the resolution to actually see it, right?
Mm-hmm. Okay. Are there more questions? Yes?
So I guess it's fermionic here, right? Because the electron gas you are using is very fermionic.
Fermionic, oh yeah, fermionic. Oh, if I haven't said that, then sorry, I have to start all over again. So yes, it's all fermions, of course, yeah. There was a Pauli principle at some point.
Is the corresponding theory for bosons trivial, or is there some concept?
No, it's certainly not trivial, because you still have an interacting system. Right, so let me try to think before I say anything stupid, but I think this thing would be perfectly well defined for bosons, and it's probably fairly complicated. In fact, you can study, I mean, this question here, I guess you can study the same thing for bosons. The F will be different, right, but I think I don't see fundamentally any obstacle. So no, I think people have, probably nobody has looked at this problem for bosons. There's maybe not any immediate application of this question, but I think it makes perfect sense mathematically.
Well, it seems that everybody needs some coffee, but before we do this, let's first thank Robert. And then let me mention that